In this session, we would be understanding atmospheric stability and instability. We have already talked about temperature and lapse rate, and lapse rate will form the basis for this session on atmospheric stability. Now to start with, I have three examples here. I have a ball which is in three different situations. This will help us understand first of all the terminology, that's stable, neutral and unstable. Now what would happen if I give a small impulse to this ball? What would happen? It would try to return back to its original position. So if I give an impetus to this ball or an impulse to this ball, it would return back to its original position, that's the center of the valley. So this condition is known as stable condition. The next is an unstable condition. That means if I give a certain amount of impulse, this ball will move and that would move only in the direction of impulse. So if I have given an impulse in this direction, the ball will move in this direction. However, if I give an impulse in this direction, the ball will move in this direction. So that is considered as an unstable equilibrium. Now understanding what is a neutral equilibrium. Under a neutral equilibrium, if I give an impulse, what would happen? The ball will move and it would remain in a disturbed position. That means if I provide a small impulse, it will move a small distance. If I provide greater impetus or greater impulse, it would move to a greater distance, and that is what is a neutral equilibrium. Now, understanding the stable and unstable equilibrium in terms of atmosphere is important. So, when I say atmospheric stability, what does that mean? Atmospheric stability, in simple terms, I can demonstrate that it is an air parcel which is much more denser or much more heavier than the surrounding air. As a result, it tends to fall down to its original level. So a stable equilibrium or a stable atmospheric set would have an air parcel which is denser than the surrounding air, and because it is denser, it would tend to fall down or move back to its original position, and that's considered as a stable atmospheric system or atmospheric stability. When I talk about instability or unstable atmosphere or instability in atmosphere, I can explain it in two terms. It can be absolute instability or it can be conditional instability. Now what is the difference between absolute instability and conditional instability? When I say the environmental lapse rate is greater than both the dry adiabatic lapse rate and the saturated adiabatic lapse rate, then we say atmosphere is in a situation of absolute instability. That means since the air would be lifted when it is cooling, and it would lift slowly because it will be warm. Okay, and once you are lifting the air, the less dense air which is there would rise at a higher altitude as compared to the more dense air, and that is what is absolute instability. And then you have conditional instability that we will discuss later when we move on to the section on conditional instability. Now, understanding how can we calculate slope or the rate. Now this is the most important section where most of the students are confused. To understand this, we have a diagram. You have the actual atmosphere, actual temperature of the atmosphere and the temperature of the air that is rising onto the surface. Now, how do we say this would be the ELR, for example, and this would be the DALR or the dry adiabatic lapse rate. Now how do we say which is more in this graph? So when we are trying to understand the lapse rate or the rate of fall in temperature, we don't just do it by means of the vertical or the horizontal distance covered, rather we understand the slope of the graph. So here for the ELR, this is the slope of the graph, and for the dry adiabatic lapse rate you have this as the slope of the graph. Now comparing these two, I can say the slope of the dry adiabatic lapse rate is more as compared to the ELR or the environmental lapse rate. So this particular graph, I can say, shows that ELR is less than dry adiabatic lapse rate, and this is a case of atmospheric stability in dry air, because we are talking about the dry air parcel. So the main thing to understand here is, a lot of students get confused saying that the ELR graph is on the right hand side, so the value of ELR should be more. It's not the case. I repeat again, because we are considering the slope of the graph here, and the slope of the DLR is more than the environmental lapse rate. Therefore, we can say environmental lapse rate is less than dry adiabatic lapse rate in this case. Now understanding stability in terms of dry air and cloudy air. So to best understand this topic, what we have done, we have divided this section into three subsections. That's the stable conditions or the stability in dry air, stability in cloudy air, and the conditional stability case. So first we will proceed with stability in dry air. Now when I say stability in dry air, that means we are talking about an adiabatic system, as we talked about in the environmental lapse rate, where there is no heat exchange from the surrounding, and in such a case we are talking about an air parcel which is moving up as it is getting warmer, but it is moving only in the cloud free area, or it is moving till the point there is no moisture that is coming up in the air parcel, or in simple terms I can say till the air parcel is unsaturated. So that point, till that point where the air parcel is unsaturated or does not have any moisture content, would be considered under stability in dry air conditions. Now what would happen? I say that the air parcel is moving up. Say supposedly you have the air parcel at a temperature of 10 degrees Celsius here, at a height of 3000 feet, let's assume. So whatever I am doing here is based on assumption, it's not the real data that I am using. So let's say at a height of 3000 feet, the temperature drops to 1 degree Celsius. Now this 1 degree Celsius is the temperature of the air parcel that I am talking about. Now what would happen at this temperature? There can be three cases. So we would be considering stability in dry air under three cases, and again stability in cloudy air and again under three cases. So let's say case A. Under case A, what I am saying is the mass of air is at a temperature of 1 degree Celsius. However, the surrounding air is much warmer as compared to this air parcel, because the environmental lapse rate or the drop in the environmental lapse rate is not that much. So I can say environmental lapse rate here is less than the dry adiabatic lapse rate, because the fall in the air parcel, the temperature fall of the air parcel is much higher as compared to temperature fall of the surrounding, which say is only 4 degrees Celsius. In this case, the atmospheric condition would be stable. So that's the case A, which is stable atmospheric condition, considering the surrounding conditions. The next is case B. Case B says the rate of the drop of the air parcel is equivalent to or same as the rate of the drop of the atmosphere or the atmospheric air. So I say the atmospheric lapse rate is equal to the dry adiabatic lapse rate. So say the air parcel is dropping from 10 degrees to 1 degrees, and similarly you have 1 degrees in the surrounding. So you have the same drop rate for both the cases. This case would be considered as a neutral atmosphere. And finally you have case B, case C. Under case C, we would say the drop in the atmospheric pressure for the air parcel is much less as compared to the environmental surroundings, where I say the drop in the surrounding is much higher. So let's say it goes below 1 degree Celsius. That means the air parcel is still warm and it would continue to rise up. That means it is in a state of instability, or I can say if the environmental lapse rate is more than the dry adiabatic lapse rate, the atmospheric conditions would be unstable, and that means that the air parcel is still warm and it will continue to rise. So these are the 3 cases that we discuss under dry air. So the first thing that we talked about is dry air. Now when we talked about environmental lapse rate, we knew that as soon as you have moisture that comes in, the air parcel reaches the dew point, and when it reaches the dew point, it's the saturated lapse rate that we would be talking about. So it's the saturated or the moist adiabatic lapse rate that we would be discussing. When there is cooling, this cooling is due to the water vapor which is present in the cloud, and condensation of the water vapor takes place, which leads to formation of droplets, and this formation of droplets would lead to latent heat of condensation. This would lead to heating, or latent heat of condensation would be released in this process. So this is the next stage where we are talking about the cloudy atmosphere, the point where cloud formation has started. And the point where cloud formation has started, we say that we have shifted from the dry adiabatic lapse rate to saturated adiabatic lapse rate. So under cloudy air conditions, again we will consider 3 different cases. So first is the case A. Let's say when I am moving up in a saturated adiabatic lapse rate, my air parcel moves from 10 degrees Celsius to say 5.5 degrees Celsius. Now what would happen in the first case? The bubble or the air parcel is at 5.5 degrees Celsius. However, the surrounding air is at a higher temperature, that is say at around 7 degrees Celsius or 8 degrees Celsius. Then what would happen? The bubble would be cooler than the surrounding. Since the bubble is cooler than the surrounding, it will try to sink back to the original position. So you have the case A where the environmental lapse rate is less than the fall in the saturated lapse rate. Now we are talking only about the saturated conditions. So saturated lapse rate, that means if the temperature of the bubble, the rate of fall is less as compared to the is more as compared to the environmental lapse rate, that means the surrounding temperature you have much higher as compared to the temperature of the air parcel. That means the air parcel would be cooler, and since it is cooler, it would tend to sink down to its original position, and it means it is a stable condition. Case B, again, where I say the environmental lapse rate, the fall in the temperature of the air parcel and the atmosphere is same. So I say ELR would be same as the saturated lapse rate, and in this case this would be a neutral atmosphere. However, finally you would have again case C, similar to what we have discussed previously. Under this case, what would happen? The bubble is at a higher temperature as compared to the surrounding. Since the bubble is at a higher temperature, it is much more warmer than the surrounding, and since it's warmer than the surrounding, it would continue to rise, and since it would continue to rise, that means you would have a unstable atmosphere. So you would have a air parcel which is at say 5.5 degrees Celsius, but the surrounding atmosphere is say only at 4 degrees Celsius. That means the air parcel is much warm. Since it is much warm, it would tend to rise further, and this would be an example for the unstable atmosphere. So these are the 3 cases that we understand, both under the dry air and the cloudy air. Now let's move on to the conditional unstable case. The conditional unstable case, as we said, we will discuss later. Now let's come on to the conditional case. Under the conditional case, I say the environmental lapse rate in this situation is less than the dry adiabatic lapse rate. However, it is more than the saturated adiabatic lapse rate. How do we understand this? Say let's say for example the surrounding air temperature is at 7 degrees Celsius. However, you have the air parcel which is at a lesser temperature than this. That means you would have a stable condition in dry atmosphere and it would rise to a height until it reaches the surrounding temperature. However, if the bubble is in a cloudy condition, what would happen? Since it is much warmer than the surrounding, it would tend to sink back, it would tend to rise back because it is warmer than the surrounding air. Since it is warmer than the surrounding air, it would tend to rise, and this situation would be unstable. That means I can say in cloudy conditions it would be unstable, however in dry conditions it would be stable. That's a simple way to explain conditional instability in this case. Now let's understand how the stability works. So these are the two diagrams that explain the dry adiabatic lapse rate and the wet adiabatic lapse rate. So what is happening here is you have the temperature of the atmosphere and the temperature of the air mass. The temperature of the air mass is falling from 30 to 0 degree. However, environment is falling from only 30 to 18 degrees. That means the fall in the environmental lapse rate is only from 30 to 18, that is 12 degree fall. However, the fall in the air mass or the air parcel is 30 degrees Celsius. That means the fall in the air parcel is much higher. That means environmental lapse rate is less than the dry adiabatic lapse rate here. Similarly, under moist conditions, what would happen? You have the fall in the atmosphere, that is only 12 degrees Celsius from 30 degrees to 18 degrees. However, the air parcel is falling from 30 degrees to 12 degrees, that is 18 degrees Celsius. So again you have the environmental lapse rate which is less than the saturated lapse rate, and in both the cases you have stable atmospheric conditions. Now let's understand the unstable atmospheric conditions. As you can see here, under an unstable atmospheric condition, what would happen? The drop in the environmental lapse rate would be much higher or more than the drop in the air parcel. So the atmospheric lapse rate is dropping from 30 degrees to -3, that's around 33 degrees Celsius. However, the air parcel is dropping only 30 degrees Celsius. That means the drop in the environmental lapse rate is much higher. Therefore, the graph of the environmental lapse rate is steeper as compared to the dry adiabatic lapse rate. So the dry adiabatic lapse rate, the slope is less steep as compared to the environmental lapse rate. For environmental lapse rate, you have a steeper graph. That means environmental lapse rate is more than the dry adiabatic lapse rate. And similarly, we go for the moist conditions here. So you have 30 degrees to -3, that's again 33 degree drop in the environmental lapse rate. However, the air parcel is dropping only 18 degrees Celsius, that's from 30 to 12. So you have a much difference or a higher difference in the steepness of the graph. The steepness of the environmental lapse rate is much higher as compared to the saturated lapse rate. Similarly, if we talk about the stability conditions and we look at this diagram, you would see how the air rises and you have the dry adiabatic lapse rate. At a point of 0 degree, you have cloud formations that takes place, and once the cloud formation takes place, you have the wet adiabatic or the saturated adiabatic lapse rate. Both these lapse rates are much steeper than the environmental lapse rate. Therefore, we can say under absolute stability, environmental lapse rate would always be less than the adiabatic lapse rate, and this adiabatic can be either dry or saturated. If we move on to unstable conditions, we will see that the environmental lapse rate is much higher than the adiabatic lapse rate. It can be either dry adiabatic or wet adiabatic. In both the situation, if the environmental lapse rate is much higher than the adiabatic lapse rate, that means you have an unstable atmospheric condition. Finally, moving on to the conditional stability. Under conditional stability, you can see the line of the environmental lapse rate crosses the dry adiabatic lapse rate at a certain point. So, you have at a certain point that the environmental lapse rate is less than the dry adiabatic lapse rate because it is less steeper. However, it is more than the saturated adiabatic lapse rate because it is less steeper as compared to the environmental lapse rate is more steeper as compared to the saturated lapse rate graph here. So, that is how we understand the conditional instability. Now, moving on to another important concept, that is stability and air masses. If I talk about polar and Arctic maritime air masses, so we would understand these under three categories. The first is polar and Arctic maritime or marine air mass. So, under this air mass, what would happen? You would have movement of water from cold source to warm source, that would lead to conditionally unstable conditions. So, there would be strong vertical movement of winds with formation of cumulus clouds. So, you would have conditional unstable condition with formation of cumulus clouds, and this cumulus cloud would lead to orographic rainfall. That is the first case. The next is the tropical maritime. The tropical maritime, you would have movement from the subtropical region to the polar areas. Since there would be movement from the subtropical region to the polar areas, what would happen? You would have a kind of dry atmosphere. Since the atmosphere would be dry or cloudy, either atmosphere, you would have absolute stability. Since there would be absolute stability, in this case you would have well arranged layers of clouds that could be seen. So, it could be in form of altostratus, nimbostratus or cumulus cirrostratus clouds. So, all these are stratus clouds or layered clouds which are example of stable atmospheric conditions. We have already discussed these cloud formations under a separate session on clouds. The final you have is the polar and the tropical continental. So, you have polar and the tropical continental landmass. So, when we talked about air mass, we talked about the concept of stability. Now, once again, this would be based on the time of the year when we are talking about and the surface temperature from the source. Based on that, based on the two things, that is the surface temperature and the time of the year, we can say whether you would have a stable atmospheric condition or a absolutely unstable atmospheric condition, like over deserts you can say would be an absolutely unstable atmospheric condition because there would be a lot of warm air rising up. Finally, this is the concept of Tephigraph, which is not important for the point of view, I could say, for civils preparation, but definitely important for those preparing for earth sciences or CSIR examinations. So, Tephigraph we would be discussing more in a separate session because it is dedicated to CSIR students. So, you have a Tephigraph. For now we will just touch it in brief. So, it is a graph between the temperature and the potential temperature. Now, what is potential temperature? Potential temperature is a temperature that the air mass could have if we are moving, if it is moved to a dry adiabatic level where the pressure is around 1000 hectopascal. So, what is important to understand here is we are moving to a air parcel which is at a which is dry adiabatically, and the diagonal lines here denote the dry adiabatic lapse rate. However, the curved lines denote the saturated lapse rate. So, we will be covering this Tephigraphs in more detail, and you can also check out the theory that would be below this video for more details on Tephigraph. And finally, in the next session we would be covering further topics which are fronts, jet streams and general monsoon conditions. We have already covered the Indian monsoon per se. We will be considering the concept of general monsoons and how monsoon affects the climate of the region. So, you can subscribe to our channel for any further updates. Have a good day ahead.